have 25 minutes.
Thank you very much. I would like to thank organizers for organizing the second edition of this conference. And today I will talk about something that is related directly with the title of the conference, namely one parameter semigroup, which appears in one particular physical situation, which is called quantum collision model with correlated environment. So this talk is based on a recent preprint that appeared last week on arXiv. So many details are there. So what is the physical problem we address? It is a problem when a system in question interacts with some structured environment. A system is denoted by capital S, environment is denoted by capital E. So the structured environment can be some multi-photon state which exhibits correlations, so among time bin modes. So radiation can be divided into time bins, and there can be correlations among those time bins. So in this case, that environment is correlated, and then the system and environment can experience evolution. And this evolution can describe excitation of the system and absorption of the photon, or vice versa, emission of the photon due to the transition from the excited state to the ground state of the system. So this is a situation, physical situation A. Another physical situation B happens when some information carrier, for example, spin, propagates through some correlated one-dimensional structure, interacting with each node of that one-dimensional chain in ballistic regime. It means that the motional degrees of freedom of that particle are not affected, but the internal degrees of freedom are affected by those interactions. And it's interesting to calculate the spin at the output of that one-dimensional structure, so to calculate spin current in a sense. And those two physical problems, A and B, motivate us to consider the general mathematical problem when a system in question repeatedly interacts with the environment, and that environment is correlated. Correlations can be either classical or quantum, and the question is, what is the dynamics of the system density operator? So computational problem is hard because the reduced density operator of k environmental modes or particles is given by a density operator rho, whose dimension scales exponentially with k. So the larger the k, the more complicated is the description of rho, and in turn, since we have unitary interactions of the system with each particular particle of the environment given by those u, it means that we should, in principle, consider that operator whose dimension grows also exponentially with k, and then take partial trace over that environmental degrees of freedom to get the system density operator. So the correlations significantly complicate the calculation of the density operator. So this problem is, of course, not the first one that was considered by physicists. So much simpler models were considered before. And the first I'm aware about is the paper by JSC Thoreau, published back in 1963, which considered the case of uncorrelated environmental particles, and in an appropriate limit, Markovian dynamics for the system rho was reproduced, and the generator was found. A review of this original paper and many papers that followed it is given by two recent papers here. The first one by Ciccarella and co-authors was published several days ago on February 12th, and another by Campbell and co-authors and co-author Vakini was published last year. So these two review papers instructively review the history of collision models. And they also mention some approaches involving correlated environment, but this research was rather limited. So only some special correlated states in the environment were considered before. One of them in that paper published in 2012 considered GHZ like environment and particular unitary interactions of controlled unitary type. So the solution was considered only in that special case. And another paper dealt with some correlated states Xi that were of direct sum form. So it's also rather limited, that approach. So if we come back to the original problem I formulated, it has some physical motivation, and the existing approaches can also be mentioned here in this regard. For example, recently a paper by Dabrowska and co-authors studied the evolution of the system due to interaction with a single photon wave packet. And that single photon wave packet was considered as an excitation of electromagnetic field, which is spread among many time-bin modes. And the solution of the problem is rather complicated, though it exists. But when it comes to multi-photon states, or some states that don't have a specific number of photons, then we expect the solution would be rather complicated. So there is a need to find some simpler solution to the problem. So here on the right side of the slide, there is a citation to the paper which studied spin transport through one-dimensional structures, and they used density functional theory to calculate that spin transport. So also these calculations are quite complicated, and some simpler solution would be quite beneficial. So let us consider one of those problems in more detail. So what makes it so complicated? So the complication comes from the entanglement in the single photon wave packet. So here you can see the state psi, which is a linear combination of one photon excitations in time-bin modes. So here one refers to the excitation in the first mode and no excitations in the other modes, and so on. So it is a kind of generalization of W state, which is very familiar to quantum physicists. And surely this state is correlated, and those correlations affect the dynamics of the system. But we can simplify the description of that correlated state if we use a simpler formalism. So this simpler formalism is based on the product introduced here. So when we have two matrices, then we can multiply them in this form. And if we apply that formalism to ket vectors, then we simply get the description of the ket vector. And if we continue somehow adding matrices in between, then we get a more complicated structure, but it reproduces the state we are interested in. For example, if we look at the bottom of the slide, you see that if we multiply matrices this way, then we reproduce the three-mode state, which describes a single photon wave packet among those three modes. Surely the number of modes is unlimited. Then we take a product of those matrices, of those n matrices, and it gives us the description of the state psi. Since we have a product of matrices, this state is also called matrix product state, and it is given by a particular tensor diagram shown here in the middle of the slide. Here, blue boxes represent respectively the left matrix and the right matrix, which are row matrix and column matrix, and green boxes describe square matrices in the middle. And you see that in our description of matrices, we used ket vectors, and that ket component is absorbed by additional index I, which is a so-called physical index of the network, whereas A is a so-called virtual index over the network, and virtual indices are summed over. So a description of that matrix B, so now we can specify it. If ik equals 0, then we look at the contribution of ket 0 in the matrix, and it gives us the first matrix. And if we look at the contribution of ket 1, then we get the second matrix here. So now we understand how to treat those B's. So B's are actually rank 3 tensors that have 2 virtual indices and 1 physical index I, and fixing that index I actually fixes the ket vector in the decomposition of the state. So any matrix product state can be written by the formula written here at the bottom, and the product of those matrices gives a coefficient that provides a decomposition of the state psi. And the general statement is that any state psi E can be written in this form, which is quite surprising, but such a decomposition always exists. And those matrix product states are not only of fundamental or mathematical interest, they can actually be created in laboratory, and there are some references to physical implementations of those photonic matrix product states. So now we come back to the tensor network formalism. So we already discussed what is subfigure A here. It is a description of a pure state, psi, describing the environment. So if we are interested in the density operator, psi E, then it is given by 2 vectors. One is a ket vector here on top, and the bra version of that vector on the bottom. And you see that I use star to denote complex conjugation of matrices used in the description of the state. So I also use arrows. So outcoming arrows correspond to K components, and incoming arrows correspond to bra components. So this is a simple description of the density operator. But if we want to calculate the density operator after K collisions, so say here, then we should consider a reduced density operator. So how shall we find the reduced density operator? We should trace over the degrees of freedom that are not relevant to us. So for example, K particles are here, and we should take partial trace over the particles we are not interested in, so some kind of future particles. So we just merge legs of the tensors. So that operation, it corresponds to the partial trace of the particle K plus 1 and so on. And you see that this diagram is quite lengthy and can be also difficult to calculate in general. But the situation becomes much simpler if the tensor network is written in so-called right canonical form. So that contraction becomes simpler in the right canonical form, and right canonicity is given by this equation, which can be always satisfied too. And then that contraction reduces to the identity operator. You can also notice that I changed the order of arrows here in the diagram. It is possible to do. Simply, I should change the matrices, and here transposition sign arises. So if I change the order of product, then I just apply transposition of matrices. And you also see that additional object chi0 appeared here. In literature, there is a description of that in the form of so-called dummy operator. So in our case, with a pure environmental state, you can think of 1 times 1 matrix, which contains only single element 1. So it is also a matrix, a trivial one, but chi0 can describe that case. And if the environment is mixed, so the state of the environment is described by a mixed density operator, then that chi0 is non-trivial. So rank of the environmental state equals the rank of chi0. But that chi0 always exists. So you can consider the figure D here as the most general description of the environmental state in terms of tensor diagrams. And this gives us a reduced density operator for K particles, which is exactly presented in the original problem formulation. So you see that density operator rho 1 and so on K is given now by this simple tensor diagram in some figure D. And now we can construct the tensor network for collisional model. So you can see here the bottom of the diagram. It is the density operator of K environmental particles. And now our system starts interacting with those particles. And after K collisions, we are interested in the density operator of the system. So this is a tensor diagram for that. And you see that at top of the diagram, there are those U terms, which correspond to the partial trace over the particles. So it is partial trace over the particle that the system has already interacted with. And now, if you look at that diagram by 90 degrees, so if we change the angle with which we look at this diagram, you can see that effectively we start from some operator of this form, and then this operator evolves while propagating to the right. And that operator is denoted by capital R, K tau, and it satisfies the initial condition that rho R0 equals rho S at the initial time moment, tensor chi0. And then we just need to propagate it to the right. So contract the tensor network after K collisions. And then we should take partial trace over the bond degrees of freedom. So this partial trace is given by the right diagram here. So this is a partial trace over the bond degrees of freedom. With this perspective, we now see that evolution of the extended operator R is given by this map E. So E, diagram for this E is given here, and the recurrent relation for R is here on top. So let us look more closely at this E. So you see that I can divide it into 2 parts. The first part is this element, and a complementary element will be here. And those elements describe Krauss operators of the map. So here it is a Krauss operator for E. And that means that EK adopts this representation where AJK is a Krauss operator given by this formula. And what is much more important is the fact that the sum of JK, AJK dagger, AJK equals identity operator because U is unitary and B satisfies the right canonical form of the matrix product state. So E is completely positive and trace preserving map. And since R is a density operator for system and bond degrees of freedom, then the evolution of operator R is given by those channels, completely positive and trace preserving maps. And it is exactly the manifestation of the Markovian embedding. So we sequentially apply completely positive trace preserving maps to the extended system bond density operator R and have the dynamics. And this leads to the following mathematical theorem. So the system density operator dynamics is given by such a formula where R evolves according to that equation. Here there is a mistake. R0 is given by rho S0 tensor chi0, where each E is a quantum channel that is completely positive and trace. Here it should be preserving map. Sorry for the mistakes. Preserving map with Krauss operators of this form. So this is a mathematical formulation of the Markovian embedding. And now I will give some examples. So the left part describes the interaction of our system with a two-photon wave packet with exponential decay times. So in between the photons and also the appearance of the first photon. So such a state is produced by cascade emission in physics. So it has some implementation in practice too. So I will simply show the excitation probability for the atom if it was originally in the ground state. So you see that blue curve shows us the solution based on the tensor networks which describe correlations in the environment. So this state is correlated. If we disregard correlations, so if we artificially replace rho 1 and so on k to the tensor product rho 1, rho 2, and so on, so which is tensor I from 1 to k rho I, then we will get a black curve here. So if we simply disregard correlations, then we have a completely different answer to the question, to the excitation probability. So this figure illustrates the great effect of correlations in the environment on the system dynamics. On the other hand, in the right-hand side, we have another example of photonic cluster state, which has a particular realization in matrix product form. And here you see also two situations. So blue curve shows us exact solution, when correlations are taken into account. And black curve shows us disregard of correlations. So when the environment is given by the tensor product of individual modes. So you see that the solutions are quite close. They are close not only in the case when the interaction strength is moderate, but also in the case when the interaction strength is close to 1. So you see that there is some deviation, but that deviation is not that great as it was here in the first picture. And the natural question arises, why do we have such a big difference here on the left? And why we have so small difference between approximate and exact solutions on the right? And the answer to that question is actually in the correlation functions of the environment. So although both cases deal with correlated states, But correlations in the first example on the left decay slowly in time, whereas correlations in the on the right hand side, they decay very rapidly. Actually, this is the reason why first two interactions give, you see, the same results. So first two interactions coincide. And the analysis of those correlations are easy to perform when the Nakajima-Zwanzig projection formalism. So I don't have much time to describe it in many details. So I will simply say that the conventional approach to the operators should be a little bit modified to get a physically clear answer. So operators chi here in the description of projections should be satisfying that figure E in the tensor diagram, which represents free evolution of bond degrees of freedom. So you see that there was no ancillary system in the original formulation of the problem. But here it appears for bond degrees of freedom. Bond degrees of freedom are here. And free evolution for those bond degrees of freedom, it is given by the diagram. So projections should be modified in this way. And other constructions inside the derivation of the Nakajima-Zwanzig equation, they are the same. So I will skip them. So I will skip the calculation. I will simply interpret the final result. So we got a kind of discrete time version of the Nakajima-Zwanzig equation, which has a local contribution, which describes the latest interaction, and also has some memory effects, so memory kernel. So memory kernel also looks quite complicated, so but it can be simplified in the second order perturbation theory. So in the second order perturbation theory, kernel becomes simpler, and it is related with correlations, with 2-point correlations in the environment. So formula here at the bottom should be taken. And what is new since my talks at other conferences? So the new is the stroboscopic limit. So the general statement is the following. So if correlation length in the environmental state is finite and the environmental state is homogeneous, so the operators bk and k don't depend on k, then we can define the stroboscopic limit, and it reduces to semigroup dynamics of the system, but the generator will be given not only by the latest collision, which is described by that local term, but there will be an effect of all previous collisions, and that effect has the strength of that number here. Plus minus originates from the sign of the second largest eigenvalue of the transfer matrix, but I didn't describe the transfer matrix here in the talk. So more details on the derivations are in the preprint. So, and with this example, I would simply like to show two effects. So suppose the environment is in correlated state. If we disregard correlations, then we have the black line. If we take correlations into account, then we have a completely different evolution of the system. You see that increase in the depolarizing parameter, and it is indication of non-Markovianity. But as we already know from the theorem, there is a Markovian embedding, and it is nice. But if we now tend jt to 0 and j squared tau to constant, so stroboscopic limit. Then we can describe that situation through the modified generator L given here. And for another example, dynamics with that L is given by continuous line read here. Of course, we cannot somehow compare the limit with numerics. So here JT is 0.1, if I remember correctly. So I summarize. So we present a general solution to the quantum collision model with a correlated environment, and our solution is based on representing the environment in terms of the tensor network called matrix product state, which is written in a right canonical form. We find the natural Markovian embedding for the system and bond degrees of freedom within the tensor network. So I showed you the embedding map EK and its Krauss operators. And correlations are taken into account by Nakajimi-Zwanzig equation. Correlations become visible in the second order perturbation theory. And if we consider the stroboscopic limit, then we reproduce Gariny-Kosakovsky-Sudarshan-Lindblad master equation, but the generator L will have still a contribution from correlations in the environment. So there will be a contribution from correlations of the environment. So thank you for your attention. That's it.